Lab 2, a falling sock. Here's the tracker setup. The video was recorded at 30 frames per second. I taped a 15 centimeter piece of cardboard to the door so that I could add a calibration stick. In SI units, this is 0.15 meters. The origin is located at the center of the sock when the sock had zero velocity just before it was dropped. The y-axis is aligned such that the sock falls along the negative y-axis. I think the camera was slightly tilted, so I had to tilt the coordinate system a bit to align the axis with the direction of motion. And here's the motion. Here are the data points taken from tracker, with observed position shown on the negative y-axis and time on the x-axis. We can see from the slope of the curve that as time progresses, the rate of change of position, which is velocity, increases. That means the sock is accelerating. Newton's second law of motion allows us to predict a future velocity after delta t has elapsed if we know the initial velocity. And in the case of the falling sock, we do know the initial velocity. It's zero. While the sock was at rest in the instant that I let go of the sock, we observed that it did not remain at rest. So the final velocity is not zero. Delta t can't be zero, and we also know that the mass can't be zero. Therefore, the only way that the final velocity can be not zero is for the net force to not be equal to zero. Because the sock did not remain at rest, we know that it was interacting with at least one object in its surroundings. And since the sock was falling downward, we can guess that the sock is interacting with the Earth. The Earth is exerting a weight force on the sock. Gravitational force on a system due to Earth is called weight force. Like all forces, the weight force has a magnitude and a direction. Remember, the origin of the coordinate system is at the center of the sock when the sock's velocity is zero, just before it starts moving down the negative y-axis. The negative y-axis extends right through the very core of the Earth. The direction of the weight force, represented by W hat, is equal to negative j, and the magnitude of the weight force is directly proportional to its mass, where g equals 9.8 meters per second per second. Putting this all together, the weight force is equal to negative mgj. We can almost calculate the weight force on the sock. All we're missing is the mass of the sock. In SI units, that's 0.054 kilograms. We now have enough information to build a computational model with Python based on the assumption that weight force is the only force acting on the sock. The Python program needs the mass of the sock. I'd like to use Python comments to keep track of the units I'm using. In this case, I'm using the SI unit for mass, which is the kilogram. Remember, we set up the coordinate system so that the sock's initial position would be at the origin, and the sock's initial velocity was zero. The Python code to simulate the sock's motion is contained inside a while loop that starts with initial time t equals 0 seconds, repeating the code each time with small increments of delta t equal to 0.001 second. The information about when to start and terminate the while loop comes from the observed data in tracker. Inside the while loop, we employ Newton's second law of motion to update the velocity with each delta t, taking into account the net force on the sock. This updated velocity is used to update the sock's position. This computational model assumes that the total net force comes from the weight force on the sock due to the Earth's gravitational force. Here's the Python code to calculate that weight force, and it's assigned to be the total net force. We also have to initialize g, the magnitude of the gravitational field, and the direction, j hat. And now we can run the code and compare the observed results from tracker, shown as blue dots, with the computational prediction, shown as a red line. We can see that the model computes that the sock should fall faster than it actually did. Why is that? Perhaps our assumption was wrong. Maybe there's another force acting on the sock? Maybe drag force due to air resistance? The direction of the drag force is opposite to that of the velocity, so it's negative. One way to model the drag force is to say that the magnitude is proportional to the square of the velocity. Putting this all together, we have that the drag force is equal to b, which is the proportionality constant, times the square of the magnitude of the velocity times the velocity vector. And it's negative, because the direction is opposite that of the velocity. Notice that I haven't bothered to use a unit vector for the direction. This will impact on the value of b, but that doesn't matter since I will still be able to achieve my goal of finding a value that forces the model to fit with the observation. What do I mean by forcing the model to fit the observation? Unlike the weight force, I don't have a value for the proportionality constant b, so I'm going to discover it empirically by choosing a value of b that forces the final position of the model to be equal to the final position in the observed data from tracker. With the formula for the drag force in hand, I can simply add it to the computational model that we use for weight force. Now we have a model with two forces acting on the sock, the weight force and the drag force. I wrote a short Python program to find an optimal value for b. You can find a link to download this program below the video. In the new model, taking into account both gravity and the drag force, shown in orange, is a much better fit.